Welcome to this video on the complete stormwater drainage design process, covering everything from basic concepts to hydraulic calculations. We will walk through the steps needed to go from an initial concept to final construction drawings. The purpose of a stormwater system is the safe disposal of water without flooding, ensuring community safety and the structural integrity of surrounding assets. Our approach uses a gravity-based system, designing for partial flow capacity and including a future safety margin. The design process adheres to multiple codes, standards, and references. These include NBC 2016, CPHEEO Manual, IRC Guidelines for Road Drainage, and specific IS codes for pipes and drains. We also rely on IMD rainfall data for intensity, duration, frequency. Input data for site information is gathered from surveys and drawings. This includes site layout, plot area, existing drainage patterns, ground levels, soil type, and the levels of any nearby municipal storm drains. Rainfall parameters are critical design inputs sourced from IMD or local authorities. Key parameters include rainfall intensity, design duration, and the selection of an appropriate return period based on the project type. Catchment delineation involves dividing the site into sub-catchments based on different surface types like roof areas, paved areas, and landscape areas. The logic is that one catchment leads to one inlet or manhole. The runoff coefficient C is selected based on the surface type, using reference tables from CPHEEO or IRC. For instance, RCC roofs have a high coefficient of 0.9 to 1.0, while green areas are much lower at 0.2 to 0.3. We use the rational method to calculate runoff, Q. The formula is Q equals 10 times C times I times A, where I is the rainfall intensity and A is the catchment area in hectares. This calculation assumes peak intensity. For our example commercial project with a total area of 10,000 square meters, we use a 10-year design return period and a rainfall intensity of 90 millimeters per hour. The area is divided into different surfaces, each with an assigned runoff coefficient. Let's review the symbols in the formula. Q is the stormwater runoff, C is the runoff coefficient, I is the rainfall intensity, and A is the catchment area. This formula helps determine the volume of water that must be drained. Calculating the runoff for the roof area, with C equal to 0.95, I equal to 90 millimeters per hour, and A equal to 0.40 hectares, the resultant runoff, Q, is 342 cubic meters per hour. For the paved area, using C equal to 0.80 and the same intensity and area as the roof, the calculated runoff Q is 288 cubic meters per hour. Finally, for the green area, with a coefficient C equal to 0.30, intensity I equal to 90, and an area A of 0.20 hectares, the calculated runoff Q is 54 cubic meters per hour. The total runoff Q is the sum of all areas, equaling 684 cubic meters per hour. Converting this to liters per second, we multiply by 0.278, giving us a design discharge of 190 liters per second. For RCC pipe design, we use Manning's formula, which calculates the velocity and discharge based on the pipe's roughness, flow area, hydraulic radius, and slope. We must assume a pipe diameter since standard pipe sizes are manufactured products. The minimum stormwater pipe size is 300 millimeters. Assuming this, the flow area A is calculated to be 0.0707 square meters. The wetted perimeter P is the length of the pipe surface in contact with the water, crucial for calculating friction losses. For our 300 millimeter pipe, the wetted perimeter P is 0.942 meters. The hydraulic radius R is the ratio of the flow area to the wetted perimeter. It is a flow efficiency parameter. For our assumed pipe size, R is calculated as 0.075 meters. Applying Manning's formula at a micro level, we select values for the roughness coefficient, flow area, hydraulic radius, and pipe slope. This sets up the full calculation to find the pipe's capacity Q. Solving the terms separately and multiplying them gives a flow rate Q of 0.055 cubic meters per second. Converting this, the capacity of the 300 millimeter pipe is 55 liters per second. Comparing the required flow of 190 liters per second to the pipe capacity of 55 liters per second, we find the design is not safe. The pipe will surcharge and overflow during peak storm events. The hydraulic verdict is not safe. Since the capacity is less than the required flow, the drain will overflow, causing a risk of property and road flooding. A design iteration is required. Now, considering the required 190 liters per second, which diameter, 450, 600, or 750 millimeters, do you think is technically correct? Next, let's explore an alternative design approach, an RCC open trench for stormwater drainage engineering and capacity analysis. The design objective for the open trench is to define standard parameters, evaluate a trial size of 300 by 300 millimeters, apply Manning's equation for open channel flow, and determine its adequacy for storm events. For the 300 by 300 millimeter RCC open trench, the wetted perimeter P is calculated as the bottom width plus 2 times the side depth, resulting in 0.90 meters. The flow area A is 0.09 square meters. Calculating the hydraulic radius R, which is flow efficiency, we get 0.10 meters. Remember, a larger hydraulic radius means better flow capacity. Here is the step-by-step application of Manning's formula for the open trench, substituting the flow parameters for this rectangular geometry. Solving the intermediate terms individually ensures accuracy. The reciprocal of n is 66.67. The r to the power of 2/3 factor is 0.215, and the square root of the slope factor is 0.0577. By solving the multiplied chain, the final capacity calculation for the 300 by 300 millimeter trench results in a discharge of 0.074 cubic meters per second. Analyzing the capacity, the current trench design handles only 39% of the peak runoff. This shortfall of 116 liters per second means the trench is inadequate, and hydraulic pressure will cause surface flooding. The verdict remains not safe. The 300 by 300 millimeter RCC trench is inadequate. There is a high overflow risk and potential for infrastructure damage, requiring a redesign with a larger size. Which trench size is technically correct to handle 190 liters per second? Based on our formulas, select the size that provides the required capacity. Flooding and overflow safety is a priority. We must ensure no surcharging near building foundations, prevent backflow, include freeboard and open drains, and define overflow paths for extreme events. Sustainable stormwater measures include rainwater harvesting pits, recharge trenches, permeable pavements, and detention or retention ponds. These measures reduce flooding and recharge groundwater. Mandatory stormwater layout drawings include the main plan, longitudinal sections, cross-sections of drains, manhole and catch pit details, and specific invert and cover level information. Drawings must clearly indicate ground level, invert level, and cover level. Slope and flow direction must be explicitly marked, and outfall point levels are critical for effective disposal. The bill of quantities includes items such as excavation, pipe or trench casting, and manholes. Authority approval involves submission to the local municipal body and compliance with all approved drawings. Common design mistakes include missing invert levels, flat slopes, and mixing stormwater with sewer lines. Remember, pipe sizes are assumed, checked via calculation, and then accepted or rejected, with every number derived from codes or standards. Thank you for watching this video on stormwater drainage design. We encourage you to share your calculation approach or logic in the comments. Thank you for watching this video. We hope you found this reference helpful. Please like, subscribe, and share the video with others.